Hey everyone, today we're working on the question 9 of Euclid 2023. So this question says, at the Canadian eatery with multiple configurations, there are round tables around which chairs are placed. When a table has n chairs around it for some integers n greater than 3, for example n is 6 here, the chairs are labeled 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, all around the table. So the table is considered full if no more people can be seated without having 2 people sit in neighboring chairs. So for example, we can't have someone sit in 2 and also 3. So, for example, when n is 6, full tables occur when the chair is labeled. Just highlight this. So, for example, if 1 and 4, that table is full. Or if we have 1, 3, 5, that table is also full. Because in both of those cases, no more people can sit without having to sit next to somebody. So they listed all the possibilities for when there's 5 people. So when there's 6 people and there's 5 different possibilities. So now it's asking for question 9, part A, determine all the ways in which people can be seated around a table with 8 chairs so that the table is full. And in each case, it wants you to write down the labels of the chairs on which people are sitting. Okay, so let's draw a quick diagram here. So let's draw a circle. 1, 2, 3, 4, 5, 6, 7, 8. So let's look at the maximum number of people we can seat. So if we want the maximum, that means people want to be sitting next to each other as close as possible. So if someone's sitting in 1, then someone wants to be seated in 3, 5, and 7, for example. So that's 4 people. However, if we want the minimum number of people, then we always want to space out by 2 so that no people can squeeze between you. So for example, if someone's sitting in 1 and we want the minimum number of people, then it would look something like 1, 4, 7. So in the case where there's 4 people or 3 people, we can't have any more or any less, because if we have someone instead of 4 sitting in 5, then someone can squeeze and sit on 3. So both of these, we got the minimum and the maximum number of people that can sit here. So in the case of 4 people, there's only really 2 possibilities. The possibilities are 1, 3, 5, 7, the odd numbers, or 2, 4, 6, 8, the even numbers. So these are the possible configurations for 4 people. So when we have 3 people, it's a little bit more challenging. So for example, we can have 1, 4, 7. And then after that, we can have people shuffle over. So it would be 2, 5, 8. 2, 5, 8, and this is a different configuration. So we can just keep doing this all the way until we've reached the same thing. So we can shuffle like this in a clockwise manner until we reached 1, 4, 7 again. So there's going to be 8 different configurations. For this question, it wants us to list all the possible configurations. So let's just do that. So 1, 4, 7, 2, 5, 8, 3, 6. When we reach 9, that's going to go back to 1 because there's no 9. So 3, 6, 1, and 4, 7, 2. So let's try the next row here. After 4, 7, 2, it'll be 5, 8, 3, 6, 1, 4, 7, 2, 5. Each time just increasing every seat by 1. So we rotate clockwise. So 8, 3, 6. So these are all the possible configurations for which a 8-seated table would be full. So this is for part A. Part B asks, in a full table with 6k plus 5 chairs for some positive integer k, has t people seated in its chairs. Determine in terms of k the number of possible values for t. So what are the different numbers of people that can be seated? For example, if in the part A, we could have 4 people or 3 people. So that's 2 distinct possible values of t. So part B asks, if we have 6k plus 5, what are the different, how many possible values of t are there? So t people. So again, we can look at the sparsely seated and densely seated different orientations. So for example, when we have 6, 1, 2, 3, 4, 5, 6, If we want the people to be densely seated, we will seat them in 1, 3, and 5. If it's sparsely seated, we want to seat them in 1 and 3 only. Got the wrong marker there. Sorry, 1 and 4 only. So this is a section of 6 people. And then again, we can just keep duplicating these sections. So 1, 2, 3, 4, 5, 6. Again, if we want them to be densely seated, then it's going to be 1, 3, and 5 again. If we want them sparsely seated, it's just going to be 1 and 4 again. So in total, there's going to be 6k plus 5. So each of these is 6 people. So there's going to be k section of 6. And after that, we're going to have a little block of 5. So 1, 2, 3, 4, 5. So in the block of 5, let's suppose this is densely seated and this is sparsely seated. So when it's densely seated, we want to see as many people as possible. So we probably want 1 and want 3. And then we can't highlight 5 here because 5 is actually adjacent to the 1 at the very front. So this and this are adjacent. We can't have them both be seated. So there's going to be a gap of 2 at the very end. So let's look at the case where we want it sparsely seated. So 1, 2, 3, 4, 5. So if we want them sparsely seated, we have to seat someone at 1 because otherwise someone will sit at the previous 6. And we have to have someone sit at 4. Oops. So again, in the section of 5, there's going to be 2 people sitting there. So in the dense case, there's going to be k, and in each k section of 6, each section of 6, we can have 3 people. So k times 3 plus the 2 at the very end. And sparsely seated is going to be k times 2 because there's 2 people in every section of 6 plus the 2 at the end. So how many different values of, so this is t max and this is t min. So how many different values of t are there? It's going to be t max minus t min plus 1. So this is going to be 3k plus 2 minus 3k, 2k plus 2, and plus 1. Plus 1 because we count both boundary conditions for t max and t min. So this is going to simplify into k plus 1. So there's k plus 1 different seatings for when there's k plus 1 different values of t, where t is the number of people for 6k plus 5 chairs. So that was part B. Let's move on to part C. Determine the number of different full tables when n equals 19. We don't need to list them anymore, we just need the number of different full tables. So C, we can do a similar approach to part B, where we split them into sections of 6. So 19, there's going to be 3 of these sections. See if I can duplicate this. And then there's going to be a 1 at the end. So suppose we want this to be as densely seated as possible. Just duplicate 1 for later. So that means we're going to have 1, 3, 5, 1, 3, 5, 1, 3, 5. We can't highlight the last 1 because, again, it's adjacent to the very first element. So how many people are going to be seated here? There's going to be 9 people. So is it possible for us to have 8 people? It's very possible because we can just switch one of the sections of 6 to be from densely to be sparsely seated. So for example, we have 1, 3, 5, and then we have 1, 4. And then we have 1, 3, 5 again. And again, we can't highlight the very last person. So this person can never be seated here. So this is going to be 8 people. And if we wanted even less people, let's see if that's possible. So instead of the 3 5s, we should always be trying to seat people as far away as possible. They're 1, 4, 1, 4, and 1, 4 again. But now at the end, we actually have to highlight one of the people from 5, 6, 7 because someone can squeeze in here. So how many people are there? There's going to be 1, 2, 3, 4, 5, 6, 7, 7 people. So first let's look at the 9 people case. So there's going to be 9 people, which this implies 10 empty seats. And in the empty seats, it's going to be 1, 2, 3, 4, 5, 6, 7, 8. So 8 gaps of 1 and a single gap of 2. 1 gap of 2. So how many different configurations are there when there's 9 people? We can just look at, instead of looking at the people, we can look at the gaps. So it's going to look something like 1, 2, 3, 4, 5, 6, 7, 8, and 2. So this 6 and 1, this could be rotated around the table, just like how we did in part A. We rotated the configuration entirely clockwise, 1 by 1. So we can rotate this configuration of 8 ones and a single 2 around the table. There's going to be 19 people. So there's going to be 19 different configurations. So when there's 8 people, this means there's going to be 11 empty seats. When there's 11 empty seats, there's going to be a gap of 1, 2, 3, 4, 5. So 5 gaps of 1. And there are going to be 1, 2, 3, 3 gaps of 2. So the configuration is going to look something like this: 1, 2, 3, 4, 5, 2, 2, 2. So note that the gaps of 2s don't have to be next to each other. It could be like 1, 2, 3, 4, 2, 1, 2, 2, and stuff like that. So how many different ways are there? It's going to be 7. There's going to be 8 different terms, so it's going to be 8 choose 3. 8 choose 3 because we choose where the 2s are going to be. But because we can rotate the circle, we should be dividing this by 8, because every rotation, for example, this and 2, 2, 2, 1. So these 2 that I put in the box here, these 2 are actually identical, because we're rotating the circle, and we can rotate every configuration 8 times. So we should be dividing 8 choose 3 by 8. So what is 8 choose 3 divided by 8? It's going to be 8 times 7 times 6 divided by 1 times 2 times 3 divided by 8. So cancel, 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 cancel. This is going to equal to 7. So there's 7 different ways we can arrange the 1s and the 2s. And for every way we arrange the 1s and 2s, we can rotate them around 19 times, just like we did in the case where there's 9 people. We can rotate every configuration around 19 times clockwise until it matches the previous configuration, and then it becomes the same. So that means in our answer, there's going to be 7 times 19. This is equal to 133 configurations. So in the case there's 7 people, there's going to be 2 gaps of 1. They're at the very end. And there's going to be 1, 2, 3, 4, 5. 5 gaps of 2. So it's going to look something like 1, 1, 2, 2, 2, 2, 2. So how many ways can we arrange this? Well, it's going to be 7 choose 2. Again, we have to divide by 7 because we can rotate this around each configuration around 7 times. So 7 choose 2 divided by 7 is going to be 7 times 6, 1 times 2 divided by 7. So this is going to equal to 3. And for every configuration, we can rotate the people around 19 times, because we can choose the starting point and then rotate them clockwise 19 times. So in our answer, this is going to be 3 times 19, which is equal to 57. And this is the minimum number of people we can seat, because we can't have any more gaps of 2, and we can't have any gaps of 3 at all. So our answer should be 57 plus 133, that's 190, plus 19, that's 209. So in N, we're going to have 209 different seatings for a full 19-seat table. And the answer is going to be 209. So hopefully that was clear. Thank you guys for watching, and I'll see you guys in the next video.